All right, good noon, everyone, for the final class of the whole semester. Uh, it has been a pleasure, and hopefully, this last little bit will be helpful for you. Hopefully, studying has gone smoothly. Um, I have enjoyed teaching this class and um, supporting you all, so hopefully, it's been a good experience for you all. I did send out a message today which basically said that. Um, so the grades and web courses are as up to date as possible. Um, so if you go to the grades tab, I can't because it'll show you all the grades. Um, but if you go there, you will see that your score should be as up to date as possible. It has literally everything that we've done so far. Um, the only thing it's missing is the final exam, and for the majority of you, it's missing the last quiz, which is perfectly fine because you have plenty of time to complete that. Oh, and it's missing physics I care about number 3 as well. Um, Once you complete that, I'll start scoring those. But everything else is in there, so you should be able to see where your grade's at. Today is the withdrawal deadline, so if for whatever reason you decide you need to do that, today's the last day. And then I just realized next Monday is actually when you decide the whether you want the grade letter or whether you want satisfactory or unsatisfactory. So you'll have your exam grade by then. So you'll have all the information, and basically, I think the rule of thumb is if you have a C, I'd go for satisfactory, unsatisfactory. If you have an A or a B, if you have an A, of course, take the grade. If you have a B, you have to decide if a B is satisfactory for you for your GPA or not. Can I update the final? The final should be updated on web courses. Um, yeah, the final is on web courses. All of that's um, we can't see what our grade will be if we mess up on the final. That should all be accurate. I'll double check that. Um, but the final should be accurate because I've currently set it to be 20%. Um, and the final is right here. So I'll double check that later. Oh yeah, I'll double check that later and make certain it's accurate. Right now, you can't put in the points for it, but you can factor that in manually, potentially outside of this. And again, I'll look into that. Okay. The last thing is I also sent in the email. Please fill out the perception of instructor. I don't ask that because the reason I ask that is purely because I want the feedback from you all. That's not used as any kind of external evaluation by anyone else. This is purely just for my own benefit, because I want to get the feedback from you all on what's been helpful or not helpful. So with that in mind, please fill that out. Give me your honest feedback. It's anonymous. If you can write in something about like specific details, what was helpful or not helpful, that does go a long way. So the more time you spend on that, the more helpful it is for me in helping to improve my teaching in the future. Yeah, and I'll see what I can do with that, Jacob. I think the concern there is the way it's set up and the way that, because it's a quiz, I can't assign points to it. Points will be assigned once I've made the whole bank, and I will actually finish that today. So hopefully that should be updated and ready by today. Okay, so today we're gonna go ahead and finish up the final review thing that we are working on. That is a lot of things. And so, reminder, I believe most of you were probably here on Friday when we went through this. But basically, we're just going to go through. I have a bunch of random questions here, and we are going to identify what the relevant concept is and then quickly outline the process for solving it. And so, we'll go through these. If I need to make more questions, I'll make more questions. So, okay. And these are just randomly selected from the problem sets, quizzes, or tests. If you have any questions at any point, please post it over in the chat, and I'll respond once I kind of reach some pausing point when solving the problem. Okay, so first off, a 25 centimeter rod's moving at 5 meters per second in a plane perpendicular to a magnetic field of strength 0.25. All of the rod, the velocity vector, the magnetic field vector are all perpendicular. There'd be a figure We can draw that figure. We have enough information here to figure out what that would look like. We need to calculate the magnetic force on the electron in a rod, the electric field in the rod, the potential difference, and the speed. So this is an interesting problem because this actually has two different topic areas. So I'll give it a couple seconds, just pause so you can pause the video if you want to work on it on your own. But if we look at the relevant concepts here, it actually depends on what section we're doing, A, B, C, or D. If we're doing A, we see here magnetic force. So the section is going to be magnetic force. It's pretty quick. If you see force, if you see magnetic force, go to the magnetic force section in your notes. Part B is the electric field in the rod. And this one is going to be actually electric, but this is going to be a little weird. It's actually easier to solve part C first and then go to B. This one is electric field / electric potential. And I'm actually going to solve C before, show the relevant concepts for C before B, because that's going to make it easier. Part C is electric potential. I mean, it's asking for electric potential, so that's where you're going to want to go in your notes, is electric potential. And part D, what is the speed of the rod? A potential difference is 1 volts. And this one, we're going all the way to Faraday's law. All right. So the first, magnetic force, that was pretty straightforward. Part B, electric field, is pretty straightforward. The fact that you need electric potential is a little bit little trickier, but when solving the problem, you'll find that that's the only way you can kind of get to the electric field. Potential difference is electric potential, so that's pretty straightforward. And the last one, how did we know it was Faraday's law? Well, if you ever see magnetic field, speed, and potential difference, if you see those three things together, magnetic field, basically if you have magnetic field, moving rod, and velocity, that's Faraday's law. Your brain immediately needs to kind of make that jump and be like, oh, if I see a magnetic field and I see a potential difference, we're going to need to use that. And actually, this is my fault, because C should actually be Faraday's law as well. So that was actually a mix-up of my own. I saw potential, and I was like, oh, it's just potential. But C is actually Faraday's law for that same reason. Potential difference, magnetic field, and a moving rod immediately go to Faraday's law. So again, I kind of caught myself there by just following that rule. Right, so for part 2, how are we going to solve these? So let's go ahead. If we draw the picture, it's a moving rod, and we just imagine there's a magnetic field like this going into the board, has some length. So for part A, the way you're going to do this is you have to remember that in this rod are electrons, and if you have moving electrons and a magnetic field, so it's a magnetic force, so the force on a moving charge is QVB times cosine of theta. Then you would find that the velocity is perpendicular to the magnetic field, so this angle is going to be 90, and actually, yeah, I have the wrong one here. It's not cosine. That's why I was really thrown off here. This is sine of 90, my fault. Sine of 90, the angle is 90, so that's going to be 1. You have the velocity of the rod. If the rod's moving that fast, the electrons in the rod are moving that fast. You know the charge of an electron, and so you're pretty much good to go there. Again, I'm going to jump to C first because we're going to reference it for B. We need to find the potential difference between the ends of the rod. Well, if you have a moving rod, this is a very specific situation, and in the notes and in the note card, there's like this exact problem, and the voltage in it is going to be voltage across the rods, across the ends of a moving rod is B times the length of the rod times V. This is L. It's the length of the rod, so that's how you do that one. We're jumping back to B because now this is where remember that the voltage equals the electric field times the distance between the ends. It was an integral before, but this was the relationship between electric field and potential. So if we find potential here, you plug that in here, and if we plug in the actual variables, it'll be the voltage, which we say is EMF in this, same thing, E times the length of the rod, the distance between them. This is a little bit of a trickier one. There's nothing, I think, quite similar to this in the final. So if you're concerned about this one in particular, I'll tell you there's not one where I'm having you do this kind of thing in the final. So hopefully it gives you some peace. And the last one is, what is the speed of the rod if the potential difference is 1 volt? So previously they gave you the velocity. Now they say, okay, hypothetically, let's do the same exact thing we did for C. But now we've given you voltage. Now you need to solve for velocity. And so that's just V equals EMF over BL. Okay, so pretty straightforward. I say pretty straightforward. This part B was a little tricky. Some of these are a little tricky, but the equations, once you get them, are all pretty simple to solve. Okay, the next one we're going to move to is, what is the net electric potential at the point P shown in the image below? Note all charges have the same magnitude, but some have different signs. So this is actually a problem that you that was on one of the tests, and this is a very easy problem for me to, instead of having point P here, I can move point P to any one of these other spots. So hypothetically, I can move maybe this positive charge over here. This is a very easy problem for me to make multiple versions of to solve. But how are you going to solve this? Well, part 1. We are finding electric potential due to charges. So that's going to be electric potential. So electric potential due to charges, you're going to go to electric potential section. If you see electric potential and the words magnetic field together, you go to Faraday's law. So just make certain that you're going to the right one depending on the wording. Electric potential has a few, just these couple sections where it actually shows up. If you see electric potential with circuits, like with resistors and capacitors, then you're going to go to DC circuits or AC circuits. Okay, so we go to electric potential. We then say that, the voltage is going to be the sum of, we'll call this RI, QI. We have to add up the potentials due to every single point charge. So every point charge makes a potential here, and each one's going to be different. So if I call this one 1, this one 2, and this one 3, this says that I need to add V1 plus V2 plus V3 at this point P. It has to be at this point P. And so you can see here, well, in our case, the charges were all the same, except the magnitude changed. But the distance also changes. So V1, if we solve this, is just going to be K times Q over A, because the charge is Q, the distance is A. V2, we still have, and let me move these 2 and 3s because I don't want any confusion that this is 2 times Q. All right, so the second one, you still have a charge of positive Q, but now our distance is 2A. Great. Last one, I'm putting a minus sign preemptively because this is a minus charge, so it's a minus Q, and I just move the minus out there. And now we're over 3A. Now at this point, you just have to remember how to do least common denominator. You're going to have to convert all these into the common denominator is 6A, and then add them all up, and that's what I had you all do on the test. So nothing too fancy there. Just remembering that you have to add up voltages. Okay. Next one. Current is 2 amps. How many turns per centimeter must be wound on a solenoid? That's a big keyword that you want to look for. If you see the word solenoid, that's going to narrow down what you need to look at significantly in order to produce a magnetic field of 2 e to the minus 3. Basically, when you consider solenoids, there's 2 things we're going to, well, I guess there's 3. You're either going to be talking about magnetic field it makes, you're going to talk about the inductance it makes, or you're going to talk about it in a circuit. So we just have to look at this and we see solenoid and magnetic field. So we are going to immediately say this is a source of magnetic field problem because it is a thing making a magnetic field. There was only 3 examples, 3 different scenarios of things that made magnetic field. There was a loop, there was a solenoid, and there was a straight wire. Those were the only 3 things we considered. So if you see any of these 3 and you see something about making a magnetic field, you go to sources of magnetic fields. Then how do we do this problem? Well, you would just look up the equation for the magnetic field that a solenoid makes, and that is B equals mu naught little n times I, or mu naught times big N times I over, and let me give myself a bit more room, mu naught big N times I over L, where L is how long the solenoid is. This little n is the number of turns per length. And so we have to look, what are we solving for here? We are trying to find how many turns per centimeter. So you're going to have to be careful when solving this, because when you solve this naturally, you're going to be getting turns per meter, and so you're going to have to convert that. But how many turns per centimeter? Well, we're solving for little n, because that is the turns per length. We are not solving for big N. Big N is total number of turns. And so little n equals B over mu naught I. And then you would convert N from turns per meter to turns per centimeter. And the trick to remembering how to do this conversion is you can do the whole ratio thing where you just need to cancel out. You can do how many meters are there per centimeter. We know meters to centimeters is going to be some ratio of 100, and you have to decide, am I multiplying by 100 or am I dividing by 100? And when I do these, I just think of it, I think of the logic behind it. If I have 100 turns per meter, and I want to convert that to how many turns per centimeter, well, every centimeter should have less turns. I went from having this many turns to having less turns. So I need to make the turns per meter into a smaller number. I know the ratio between meters and centimeters is 100, so I'll divide by 100. Whenever you're doing these unit conversions, that's how I personally like to do it. You can always just stick to the rules of just like, oh, I need to cancel out the units. Whatever works better for you, but I want you to know that logic is another way of doing it rather than just pure math. Okay, I'm gonna do one more and then we'll take a break. During that break, for whoever's here watching, if there's any specific problems that you want me to kind of pose, I can make up problems kind of on the spot because we're going through these. So during the break, or even think about it now, what kind of problems you would maybe like to just... Again, I'm going to go through these quick. I'm not working them out completely. But if you have an example problem, feel free to just copy and paste it into the chat, and we can kind of, how would we solve that and think through that, and I can give tips and hints, tips for how to kind of approach those. So, next one, salt crystal, distance between adjacent sodium and chloride ions is 2.82 angstroms, which is the same thing as 2.82 nanometer. What is the force of attraction between the two singly charged ions? So the nice thing about this wording, I say the nice thing, as far as teaching is concerned, I don't tell you, so we need to find, it's the force of attraction, okay? But I didn't say what the force of attraction was due to. In this class, we've talked about three forces. We've talked about, and this is basically what you're going to want to do when seeing this problem. You recall in your brain, what are the things that result in forces that we talk about? There's gravity, there's a force due to an electric field, and there's a force due to a magnetic field. So we have to look at this problem and be like, okay, are we talking about gravity? I'll go ahead and tell you, no, we're not talking about gravity. Gravity is going to be much... You could consider the force of gravity here. You could do all the math, but I'll tell you, unless... The force due to gravity is pretty much going to always be predominantly weaker, and generally you're only going to consider gravity if I specifically tell you something with gravity in the problem. So otherwise, if I don't say the word gravity, or I don't say force due to gravity, you generally don't worry about that. Because the other two forces, electric force and the magnetic force, are way stronger 99.9% of the times. So with that in mind, is it electric force or is it magnetic force? And again, this is probably pretty straightforward for most of you. If you have a charge, stationary charges, the force between charges on each other is going to be electric force. So this is an electric force problem. I'm just kind of outlining all the steps for doing this because this is the thought process you use for all your problems. What are you looking for? What variables are given? What relevant concepts are at play here? So if we're talking about force due to attraction, And we would even draw these. So here's my sodium ion in A, and here's my chlorine ion. Sodium is going to give up an electron. So if it gives up one, it's going to have a positive 1 times charge of an electron, and the chlorine gets a negative 1 times charge of an electron. So that's their charge, but all this to say the force equals K Q1 Q2 over R squared. In this case, the charge that they each have is just going to be K charge of an electron squared over R squared. Even though they're positive and negative, we generally just take the magnitude because we already know they're attracted to each other. So hopefully this problem is pretty simple for you to solve. This is a very one of the first ones that we've talked about in the class, one of the first kind of problems. And if this is challenging, definitely review this section because you will see problems related to the force between charges. Don't necessarily worry about determining what the charges of the sodium and chlorine is. That's chemistry. I'm not testing you on that. The things I am testing you on is you do need to know the charge of an electron is negative and the charge of a proton is positive. That's the only additional information you'll need to bring into these problems. Okay, so I'm going to give a couple minute break. So it's going to be 52 in a second. So we'll say 11:54. So a couple minutes. Feel free in that time, again, if there's any questions, if you're watching now, any questions that you're like, okay, I don't know how to do this, or I'd like some hints on how do I actually identify how to solve this, please post those in the chat, and I'll go ahead and do those during this session as well. So I'm going to go grab some water, but I'll show you my dog while I do that. Oh, gosh. Let's see. Yeah, you. You're just gonna stare at me. You can always tell where I am in the room based on where he's looking. All right, so I got some questions. So I'm gonna actually prioritize those. We'll go through the last of these, but I'll make certain, since I told you I'd go through those, I'll make certain to do that. So one of the questions was on problem set number 2, which was and I actually got this question from a few people during office hours, so it's a good one to cover. Let me jump over and just copy and paste. No, this is a little bit slower. Okay, so apologies, I just need to open up the problem sets so that I can get the exact wording for it. But problem set 2, number 4. And so this one is a circuit with a resistor and an inductor in it, and it's asking for, and again, I'm not going to work through the whole thing, but we're at least going to go through the same process of, okay, and it's going to be pretty obvious what section it's on because I'm pulling it from inductance. Okay, so this is the problem where you have this circuit, and there's a few steps with it. Oh gosh, that is, okay. All right, so if you see a circuit like this, you see a resistor, you see an inductor, this is going to be in inductors. So this is a section on inductors. It's a DC circuit, so you may think it's in DC circuits, but we didn't actually cover inductors in DC circuits. We covered these in inductors, specifically in an RL circuit. So that's kind of the subsection of inductors. And so how would you then solve this problem? Well, basically when solving this, you have to consider step A, is it charging or discharging? And I'm not going to call this A, I'm going to call this I because I don't want to be confused with these A's. Is it charging or discharging? You have to decide that. And then you choose, and then you just use the appropriate, use the Q of t or V of t for this situation. So for example, all right, let's look at this one. So switch 1 is closed. So switch 1, this is the charging. Switch 2 is actually current's going to flow the other way, and it's going to be discharging. We call it discharging and charging because we imagine the battery is like charging it up. It's not with charge, it's with current. So when switch 1 is closed, it's doing that charging. We see here, though, that initially S1 is closed and S2 is open, but then it's considering when S2 is closed. So the discharging just has the inductor and the resistor. And so it's a discharging case because there's no battery. If there's a battery, it's charging. No battery, discharging. And then we need to find the current. And so in that case, for the discharging, the current equals I max. So it starts off maximum and then it decreases with time. And that's just going to be e to the negative t over tau, where tau equals R over L. So the current's going to start at maximum. And actually, I think I may have this backwards, so I apologize. Let me double check the equation for this. E to the 0. Nope, I had that correctly. T over tau. The way to check this is literally just plug in time equals 0. So when time equals 0 here, this term goes to 1. And so when time equals 0, I have the maximum current. The other version, the charging case, is always going to have I max times that 1 minus e to the negative t over tau, and apply that same check. The same exact check, where just put t equals 0. T equals 0, this equals 1. 1 minus 1 is 0. My current is 0 at time equals 0. This one, plug in 0. E to the 0 is 1. My current at 0 is maximum. So that's a quick check for kind of figuring out which is the right equation to use. Or again, you can just look at the formula sheet and see there. So that will give you A, that'll give you B, and voltage equation. Voltage is going to decrease with time. So we're going to use voltage T equals V max times 1 minus e to the negative t over tau. And remember here that V max is actually going to be the V of the battery, because the maximum voltage this thing is going to get is the voltage of the battery itself. So that's a quick way of going through that. Dominique said, oh, the two IFT equations, yeah. So one of them is for charge. So this is discharging. This is the discharging case, and these are all written down in the slides. So if this is uncertain, go look back at the slides. You'll see on the discharging slide for an RL circuit, I give you this equation: I max times e to the negative t over tau. For the charging case, I give you this other equation where it's I max times 1 minus e to the negative t over tau. So when doing these problems, just see which case it is. Charging is when you're connected to a battery. Discharging is when you're disconnected to a battery. That same jargon works if it's an RC circuit. Same thing. Connected to battery, charging. Disconnected, discharging. If it's a closed circuit. And then you can just remind yourself which one is which. And remember that the current through the inductor is actually 0 at time equals 0 when it's charging. And it's maximum when it's discharging at time equals 0. So I recommend for this, if this isn't making sense, go back to the end of the inductor slideshow, and you'll see a bunch of slides just focused on this, and they have nice graphs that kind of show what all this looks like. So this problem, as far as like the physics of it, is just identifying what's charging and when it's discharging. And then you just use the right equation. You just use the either discharging or charging. Dominique said, for the optics problems we went over last class with the light rays from the sun, I get confused on which wording to use and which angle the question is asking for. Let me double check if any of these are like that. No, they aren't. So I could just make up a problem really quickly. I could say light enters water at a 30-degree angle to the surface of the water. What angle does the light have in the light enters? What angle does the light exit the water with? Exit into the water with. All right, this wording's not amazing, but there's just a few kind of key points here that I want to highlight. So light enters water from air at an 80. So we need both things. So light is going from air to water. So light enters water from air. So it's coming from air. So we know our light ray is coming from our air into our water. We then look at this and we see at a 30-degree angle to the surface of the water. Well, the surface is this straight line here, and it's the entering angle, so this is the 30-degree angle. And the question is asking what angle does the light exit into the water with? And this is the tricky part. Whenever we're solving these, so this is a Snell's law problem. If we do our classic little two-step process, Snell's law problems use that n1 sine theta 1 equals n2 sine theta 2. Whenever you are solving these problems, you are finding this angle. And these angles are the angles with respect to the normal. So this is the normal. This is the area vector. The area vector, the normal, they're the same thing. When we're doing the calculations, this is the angle between the light and the area vector. Theta between light and area vector. Area vector is that perpendicular vector to the surface. Every single time, this is the angle that you want to be using, and that's what this equation, you have to use those angles. So when you're doing these problems, first draw the picture, draw the angles I give you. So in this case, I said 30 degrees to the surface of the water. Surface of the water means this surface. Basically, the only time I have to use the word area vector, or the word normal for it to mean the angle we actually want to use. So in this case, because I said to the surface, that's this angle, that's the jargon here. And so I'm actually going to have to, theta 1 is going to equal 90 minus 30. Which is going to be 60. So you would plug in 60 into here. And when you solve this, you would be getting the angle between the area vector and the ray of light going into the water. So entering angle will be the top one. Exit angle will be the one where the arrow is pointed outwards and away. So all this to say, draw the picture, and the angles will be with respect to the area vector if I use the word area vector or normal. If I use basically any other wording, it's going to mean this angle. For instance, in one of the previous problems, I said above the horizon. Well, the horizon is the flat line, so it's the same thing. So long story short, if I say between the area vector, or if I say it enters the water at a 30-degree angle, if I say it enters at a 30-degree angle, I'm also referencing this because that's our general thing. If I say anything else, I'm meaning this other angle. Okay. So let's do these last few problems and we'll kind of call it closed. This one is two long straight wires, both carry current to the right. So they're both carrying it to the right and they're parallel. One carries a wire 2 amps, one carries a wire 5 amps. And how far from wire 1, if we call this one 1 and this one 2, is the magnetic field equal to 0? This is a source of magnetic field problem because we're saying magnetic field and a straight wire. Remember, the three things that make magnetic fields are straight wire, a solenoid, and a loop. We have straight wires. We are talking about magnetic field. We are saying they're making a magnetic field because nothing else says anything about that. So source of magnetic field, I'm just going to put source of B. And how do we solve this? Well, we know that the B net is going to equal B1 plus B2, and these are vectors. And so in this problem, we have to find when it equals 0. And the tricky part here is you have to remember that each of these makes a different one. So I'm going to make wire 1 blue and wire 2 red. Just going to redraw these to make our life easier as far as symbolizing things. So we have to see what the magnetic fields are at various points. Wire 1, use our right-hand rule, makes a magnetic field into it here and out of it here. And there's 3 regions, above, between, and below. We need to find where they cancel. Wire 2 makes a magnetic field out, out, and into. Again, I'm going to leave the practicing right-hand rule to you. You can see that above it, these add. Below it, they add. In the middle, they actually cancel, and that's where we care about. So you're going to set up mu naught I over 2 pi R1. And we could just say minus mu naught I over 2 pi R2 equals 0. This is the equation for the magnetic field due to a wire. So I just plug those in. They both make a magnetic field a certain amount. Let's pick some random spot. And this is R1. This is R2. The distance from the wire to the point. And the last tricky bit, which I've had you all do a few times now, is I don't explicitly give you what the relationship between R1 and R2 is. I do tell you the distance between these is 10 centimeters apart. And so you have to remember, you have to look at this and be like, oh, R1 plus R2 equals 0.1 meters. That was the trick with this one, is figuring out this last relationship. Pretty much most of the people could figure out this first one. The second one is where I saw a lot of challenges. Once you know that, you plug it in and you can solve the problem. All right, next one. What is the electric flux through a 2 meter by 2 meter plane that is perpendicular to a magnetic field of magnitude 5.6 times 10 to the 6? So this is clearly going to be electric flux. Electric flux, which technically kind of fell under Gauss's law, is where we saw that. But you can also just look through your notes for anywhere where electric flux was. We're going to draw our picture. In this case, the wording's not amazing, but if we say that the plane is perpendicular, that does mean that the area vector is parallel to an electric field. And in my problems that I'm going to give you on the test, the wording will be far more clear. I will either say the plane, the angle between the electric field and the surface is 90 degrees, or I will say the angle between the electric field and the area vector is 0 degrees. If it's between the surface This is the theta between the electric field and surface. Just draw the angle between the vector and the surface. And so if that's 90 degrees, draw your picture so that's 90 degrees. I'm going to draw E over here because it's going to be easier. I can't really draw the angle here because they're parallel. The angle between the electric field and the area is this non-angle here. Let me draw one that's a bit easier to show. Area vector E theta. This is the angle between theta between E and A. Okay. All that to say, we need our flux equation, which is just E times A times cosine of theta. And theta is always theta between E and A. So even though I said the word perpendicular in this problem, that perpendicular was actually between it and the surface, which meant that the angle between E and A is parallel. You can see that when you draw the picture. And then you just plug in the values here. Again, I've tried to be careful with the wording here. And if you're uncertain on it during the test, you're welcome to email me. And most of the time I can clarify a small detail like that. So if you catch something like that, feel free to email me during the test, and I will be doing the best I can to respond to emails during the testing period as quickly as possible. Since you have such a long time during the test, I should be able to get to you before you get back to you before you finish the test if you have some uncertainty. All right, two last ones, and then we're going to conclude it. We have an automobile with a radio antenna that's 1 meter long, which is generating an EMF. So we see EMF, so that's a keyword, which basically immediately we're going to start thinking of Faraday's law. That's kind of one of the first things. So generates an EMF and it's traveling at some velocity. So now we have EMF and velocity, which immediately EMF, velocity, you want to jump to Faraday's law. Without even reading the rest of the problem, your mind should immediately kind of go there. So at some time later, though, the antenna triples in length and the car begins traveling at a quarter of the original speed. And this is a ratio problem. So this is a Faraday's law problem. This is very similar. Same exact concept. It is a moving rod in a magnetic field. And it says the Earth's horizontal magnetic field is this. And this problem's not clear, but again, I would be more clear in an actual problem. The V and B are perpendicular. That's pretty much all the problems I'm going to give you with this. They're going to be perpendicular every single time. So this is a moving rod. So we immediately use the exact same equation, E equals BLV. And the trick to doing these problems is this is the original EMF. Our new EMF, we'll call this one E1. That's our original. It had some length, some velocity, the magnetic field. Our next one is in the same magnetic field. Our antenna has tripled in length, so we just put, okay, tripled in length, great. And it's traveling at a quarter of the original speed, so 1/4 times velocity. I literally just plugged in how those variables change. The length tripled, the velocity is 1/4. We're trying to find the ratio of the new one to the old one. And so the trick to doing that is you want to get this BLV here. So just pull out all those extra numbers. So pull out the 3, pull out the 1/4. So 3 times 1/4 is 3/4. We return that BLV because we pulled out all the extra numbers, and we see here, oh look, BLV is EMF1. That's why when you pull out the numbers, this is what you're kind of doing, is you're returning the original equation, and you see here it's 3/4 times that. So in all of these, just plug in the multiplication for it. All right, very last one. Quickly go through this. Energy stored in a capacitor. If you see energy stored and you see capacitor, this is going to be capacitance. We're talking about a capacitor. And you see energy stored, you just look at your equation and make certain you're using energy stored in a capacitor. Energy stored in a capacitor has this 1/2 term. Do not forget the 1/2 term, because the regular energy due to voltage is just Q times V. But for a capacitor, you have that 1/2. So if you see the capacitor, make certain you use the energy due to the capacitor. All right, we see here we're given the capacitance, we're given charge, so we just remember C equals Q over V. That's the other equation we use. So we need to convert this. We know voltage, we know capacitance, and we want to find charge. We do not know the energy. Oh yeah, so sorry, there's two parts here. What is the energy stored in that? So we need to convert this into one that has capacitance in it. So Q equals C over V. So we get 1/2. Something's off here. I messed that up. Sorry. Q equals C times V. So you get 1/2 CV squared. I just plug that in and you just solve the problem. That's part A. Done. Amount of stored charge. Well, if you know the C equals Q over V, you just use that same thing. Let's find the stored charge. Q equals CV. Okay. So that is the last of it. We got through a bunch of problems. And again, hopefully what I was trying to just highlight the process for solving these problems. That you want to highlight kind of the key words in it. You want to be able to look at it and see, oh, energy. So you immediately want to get your mind in what has energy. We see capacitor, so you want to find the equation for that. If you're talking about optics and there's lenses, like just know where to go in your notes. If you know where to go in your notes, you are more than halfway there, and you've restricted it to just a few equations. You've restricted it to just a few practice problems that you've done on this, and that should hopefully kind of narrow down what you actually need to do to solve the problem. Best of luck to help with. I have one more office hours this Wednesday, but if you have any more questions or anything like that, please, of course, email me. And I hope everything goes great for you all. If I see you in office hours, great. If I don't, have a good rest of your life. I hope everything goes smoothly for you. I hope this whole pandemic we're going through hasn't been affecting you too strongly, and if it is, that gets resolved in the future, that things don't go bad, and that we all can kind of go back to some stability and some normality soon. But have a good rest of the semester. I've enjoyed teaching you all, and I again hope the rest of your lives go well. All right, goodbye.